Yes.
Oh, it's going now.
Okay, cool. Shall we start? Okay, well, it's my great pleasure to introduce Phil. Dr. Philip George began his higher education in physics and choral music as an undergraduate of Magdalen College of Oxford University in 1978. He was awarded a BA in physics in 1981 and in 1985 a Doctor of Philosophy for his investigations of the outer atmospheres of late-type giant stars. Since 1991, he has worked as a scientist at the National Center for Atmospheric Research in Boulder, Colorado. He was appointed as a senior scientist at NCAR in 2004 and is currently working on understanding the basic physics of the sun's atmosphere. Driven to mentor and learn from young scientists, his research papers have a strong pedagogical slant. Often they raise more questions than answers. His 2020 book, The Sun, in the very short introduction series from Oxford University Press, has been well received by both interested laypersons and professionals alike. Philip has enjoyed many sabbaticals and visits in universities across the globe. He's been privileged to work with many students and staff. His research focuses on the foundations upon which our understanding of the sun and stars are built, from spectroscopy, spectropolarimetry, and radiation transport, to the mechanisms by which electrodynamic coupling heats and drives the plasmas surrounding gravitationally bound astrophysical objects. He is an avid flight tire and fly fisherman, a lover of international cricket and rugby, a partially successful opera singer, cancer survivor, and author of 4 fiction books devoted to the climate crisis. And throughout the time I've known Phil, he's always been a great inspiration of thoughts about what I've been doing in general. So thank you, and I'm really looking forward to your presentation.
Yeah, thank you so much, Momo. I'd like to say that I learned more from the young people than ever I learned from a textbook, and I'm going to relate some of those things. Hopefully we'll have a little bit of fun, even though this is going to be a resume of about 40 years worth of work. So, but it's not going to be terribly mathematical or deep or anything in that sense, but it's going to be a lot of physics. I'm aiming to give a talk at the level that an undergraduate who's graduating in physics would understand. And it's a real privilege to have been able to enjoy my career this long, especially at a place like HAO. The first tasks given to me when I arrived here, first of all, I came as a postdoc, and then 2 years later, I found out who my supervisor was. It was Keith McGregor. And the nice thing about that was they pretty much let you do what you wanted. The thing that I was failing to do, which they said, you know, if you want to stick around here, is try and do a really tough problem and make a difference in your research area. That was more or less the only instruction I had at HAO. And so I was delighted to have that. And being part of a national center where we don't have to teach, and yet we get a full salary here as a researcher, I knew what a privilege this was. And so I did my best to try and do that. And today I'm going to describe my failure to achieve anything in this area, but maybe with some things that I've learned along the way. So some time ago, Gene Parker quoted the Wigner's dictum, which is that the important problems in physics are rarely solved, they are forgotten or declared to be uninteresting. I don't know what Wigner was talking about in particular here, presumably something to do with quantum chromodynamics or something like this. But, and this is not quite the case for the corona. I've concluded that the corona is pretty much, and in particular the coronal heating, is pretty much taken for granted. That's a problem, because what it means is, as you'll see, I'm claiming that the instruments that we've got flying are not suited to the coronal heating problem. It's sort of an afterthought to coronal dynamics. Okay. So here's an overview. And you'll see a picture of a baby and a guy there. Who knows who that person is? The idea is to show you how long we've had this problem. This is Keith Richards from the Rolling Stones, and everybody knows that the Rolling Stones are the oldest rock group in the universe. So this program has been around for the entirety of Keith Richards' life. Okay. So coronal heating in context. So when thinking about this talk, I tried to wonder what would happen if we did not have coronal heating, to see if it mattered. Well, without the UV or X-rays accompanying this, we wouldn't have an ionosphere. And it is strictly the corona, not the transition region or anything underneath it that's doing this, because things like Lyman alpha, they happen to be in a gap in the atmosphere, and that gets all the way down before it's absorbed into the mesosphere. So the corona and the existence of the ionosphere, it owes itself to the corona and the radiation therefrom. Now, on the right, I've got a picture of Marconi's antenna from about 120 years ago. This is in the US, somewhere in the northeast of the US. Perhaps somebody knows where this is, I don't know. And anyway, we would probably have had a different World War I or World War II, maybe even Cold War, because if you imagine, without the ionosphere, what's the point in trying to communicate across the Atlantic? You can't. So what I'm saying is, that is one consequence of there being a corona, and why, if it's being taken for granted, this is a problem. Secondly, without that, we probably wouldn't have had Alan Turing working on the Enigma machine. We would have less photochemistry. Would there be atmosphere and life on Mars because the solar wind did not strip its atmosphere? Would there be advanced life on the Earth? Probably, because it originated in the oceans, we know that. But really, without coronal heating, in terms of what this audience might be interested in, there is no coronal dynamics or space weather. There's no solar wind, solar spin down, and entirely different global dynamo, perhaps, depending on whether the corona serves as a sink for various quantities that the MHD system has to obey while it's evolving. So I'm claiming that until we understand the coronal heating problem, we're not really understanding anything to do with the bulk of the emphasis in HAO right now, which seems to be on space weather applications. Okay, it's a universal phenomenon, and here are two pictures, and this is from the book, and I'll get to the book shortly, concerning what we call electrodynamic coupling. A gravitationally bound object pulls in the magnetic fields with the charges inside this object. Those charges generate by internal dynamics and nuclear fusion and what have you, turbulence and spinning. You've got a residual angular momentum. That's all that's required to generate a magnetic field extending out into the universe. And here are two examples. The left one is 10 to the 20 meters. The right one is a CME, which we're very familiar with, 10 to the 10 meters. I'm about 1 meter from, top of my head is probably 1 meter from the ground at the moment. It doesn't mean I've shrunk, it means I'm sitting down for those not in the room. And an atom is about 10 to the minus 10 meters. So you can get an idea of the difference between me and an atom, and then a CME and this jet of M87. And by the way, in the radio, that jet is 20 times bigger than that. These are examples of the coupling between the gravitationally bound energy and the thermonuclear energy in the interior object and the outer parts of it. So the next thing is to introduce this is we might consider what we might do to, first of all, to cook up such a corona. We'll get to the history in a minute. This is just an overview. And I remember once having a Bailey's chocolate cake, which I ate too much of, was subsequently not too well, but it was Christmas. Anyway, so you go through a recipe, and at the end of the day, you eat the thing. In the sun, we also have a recipe. And various recipes have been brought forward over many, many years, including things like nuclear fusion in the atmosphere of the sun. Meghnad Saha proposed that one, including things like meteorites and all kinds of funny things. But now we've got a better understanding as a result of better observations. And here is the recipe you would need to build a solar corona. The problem is that number 3 is rather tricky, because what we know about the sun and plasmas is, from classical mechanics, the magnetofluid is essentially ideal. In other words, in those two equations, equation 1, the first term dominates on all scales down to probably about 100 kilometers and maybe even meters in the sun. That means that the thing, because it's ideal, there's no resistivity. So how on earth do we get energy from something that's magnetic to do what we saw in the previous figure when the plasma is almost ideal? Okay. And here's one take on the problem. We could eat the cake and then try and figure out what the recipe was that cooked the cake. That's what kind of we're doing, and that's actually making me rather hungry. And we can observe the corona. The problem is that by eating and going backwards, we then know how to make a chocolate cake. We know all this stuff. We've got various atoms, we've got charges on them, we've got things. We have to wait over 30 minutes for the thing to cook properly. That's just a statement that a typical corona, once you've dumped heat in it, will relax on a time scale of 30 minutes or so. So we know what we're doing, except that there's this nasty little star here that says the question, what the hell are the dissipative structures? So what we've got to do is figure out how this thing, this is from the Solar Probe, the European Solar Probe mission, the EUI images, and that's the size of the Earth relative to that thing. And remember what I said, if the dissipative scales are 200 kilometers or below, look at the challenge we're facing. So first of all, we need to decide for ourselves what a valid solution might actually look like. Yeah. This is a book by co-author James Ironson. Ironson is famous and infamous. He led Reagan's Star Wars science research program after becoming disenchanted with solar physics in 1985. Very strong character. He contacted me having read a review I wrote and was so encouraging and with so much insight, I invited him to become a co-author. He then became the CEO of Kodak and has since been working on his own software company and currently lives in Massachusetts. Anyway, I was so encouraged by him, and I don't know if the book would have been finished without his encouragement. So we declare the problem to be solved when credible mechanisms for the generation, transport, and irreversible dissipation of energy have survived reputation against critical, information-rich experiments. That's a very particular statement. Every word there is meaningful to me. And if you miss some of these things when you're studying the sun, for instance, if the observations aren't critical or they're not information rich, then it's hopeless. You may as well give up. That's what I'm claiming. My conclusions are that there's a lot of information poverty, and these are subjective things. Some of these things will be uncomfortable for some of you to hear. So these are subjective things that I've found by reviewing the literature over the last, 40 years really, but recently in the last few years. We also have weak methodologies. When you observe the corona, it's a fully booked cake, fully cooked cake. You're never going to find out what led to that by just observing thermal properties. That's done. It's like observing the end of the universe and trying to find out how the universe started. All you've got is a trace of thermal, which is sort of maximum entropy condition. So when you're looking at thermal populations of things, as revealed to you in X-rays and EUV and stuff, you're looking at the end deal. You've missed the bus. You've not learned about the heating mechanism. There is unpleasantness in this business, which is well known throughout the whole of science and in other arenas, namely that of confirmation bias. You see what you're modeling in the data. But the really great thing about this is that you've got new results that can come through from these new instruments and new opportunities. So here is the current paradigm. On the left, we have all the gravitationally bound energy underneath the surface of the sun doing its stuff. And I'm not going to go into details here, but nevertheless, there's a journey as this energy moves towards the right. It does various things in this figure. And what we're looking at here is the effects of what Jim Ironson in '78 termed electrodynamic coupling. It spans 7 decades in scale, 7 decades, a factor of 10 million. 4 of which are unobservable to us. 4 out of 7. So we're really looking at just not the tip of the iceberg. We're only observing the sort of bulk of the iceberg and not the tip. The tip is a small scale thing, and the small scales are the critical part of the problem that's missing. There is very diverse physics, diverse physical regimes of plasmas. It really demands a depth and breadth of knowledge, which is kind of unusual these days. So hyper-specialization is not going to get you very far in the study of coronal heating. Even so, on the left, you've got P watts, the power of the sun radiating out into space and consuming its mass and all that stuff. The corona at most is 10 to the minus 5 of that. That means that anything observable on the left-hand side, you'd have to observe with a signals noise of 10 to the 5 to 1 to get a signals noise of 1 on the right-hand side. In other words, any tiny change in the photosphere that's 10 to the minus 5 or bigger is going to overwhelm the entire corona above in just an order of magnitude energy thing. So these are the reasons why we still have a problem, I believe, after this research. So now we're going to go over a little bit of history here and see how I'm doing. Okay. And we're going to go, this is a random picture of a funny kid with teeth and all that stuff. But there he is in 2023. And we're going to go from 1943 onwards. If I look in the research tools available, what I find is that in typing in titles, I get one article published every 2 weeks since 1943. And if I look at the abstracts, I get one article every 2.5 days since 1943. Okay. The publications, left-hand side is from 1943 through to 1970. I'm not showing 1970 is not particularly. I didn't choose it. I just showed you just chose this to show you the vertical scales. Factor of 100 difference between the vertical scales in these two plots. The right-hand side shows you the other one. Now, if you came into physics in about 1973 when Skylab went up, there's a lot of discussion about the moon and NASA and stuff now, but Skylab was a spin-off of NASA. They took one of the command modules and stripped it out and put an observatory attached to it, the Apollo telescope map, and various other detectors there, put some astronauts in it, and they observed the sun. And so in 1973, we ended up with the first really good close-up look at the sun so that we could start to identify certain regimes. And so then what you see there is that by 1974 or so, we had maybe 100 publications to go through with those titles in them. Okay, so that's kind of a lot for a PhD student to go through, but it's one every 2 weeks for the first year of their research program. Now we're up to one a day for the first year. Sorry, 3 a day on the first year, 4 a day articles to read completely if you wanted to do that. I believe that's part of a reason that we've made that our wheels have been skidding for the last actually few decades in this problem. Another interesting plot is this one. It's not to do with coronal heating, it's solar PhDs. And you can see the distribution of them from one, at least it's a database. It's not pretending to be any complete but it does. I picked out PhDs because that is sort of the start of a professional astrophysicist's career. And some fraction of them is not going to continue, some of them will. So this, I think, is an interesting plot all by itself. So we have events at the top, which are to do with ground-based observations. We go from Khartoum on the left, the eclipse, to DKIST on the right. Things like development of Solar AO. We have vacuum telescopes, the Swedish solar telescope, Gregor, etc., all scattered up there. And then the bluish ones are all to do with NASA, ending and with spaceflight, ending it with Aditya. I probably pronounced that wrong, but it's so these are the, and then you can see what's happened here. Around 1973 with Skylab, the number of solar PhDs really jumped, and that's not a coincidence, I don't think. There are various things underneath here, such as the development of the internet, stock market crash, COVID. That's a big one here, and what have you. So I think this is kind of intriguing from the point of view of a research area. I did propose to Living Reviews in Solar Physics that I write a review on methodology in solar physics based upon some of these data, and they just said no.
Well, good. Maybe you got some sun. Was the skiing good?
Skiing was great.
Cool.
Gosh, last day yesterday.
Cheryl, you're not mute.
Yeah. So you
That's a pity. I thought it was more interesting than what I was saying. Actually, I didn't understand a word of it. So anyway, here we go. 1940s, the beginning of coronal work. Okay. there's the paper, there's the person. I was privileged to meet him. The only thing he said about a talk I gave was, did Phil come on the night train? And the guy said, yes. He said, I thought so, because he's still wearing his pajamas. I was wearing shorts at the time. So anyway, that was my impact that I had on this guy. This is a beautiful piece of work. Even if it's written in German, it's really, really clever what he did. The solid lines are laboratory work, and the dashed lines are what he pieced together from the observations of the corona at the time of emission lines that weren't understood, coronium, etc. And what you can see here is this is the element, so this is the atomic number, and this is a function of the charge on the atom, -8. And so what you see here is the charges increase up here. And so when you look at this, there's no doubt whatsoever, you'd have to be crazy. Even if you only have statistics of 4 or 8 points there, you'd have to be crazy not to say something is really interesting and going on here. And so this marked the beginning of coronal physics. In the 1940s, it was believed at this point that the sun's atmosphere was probably stratified like the Earth's is. In other words, you have protons and maybe a bit of helium way up in the magnetosphere and all that stuff. But then gradually the abundances change according to the mass and the diffusion of versus gravity, so gravitational settling. This is definitely not the case in the corona. We found something called a Fibb effect much later, but it's like a first order correction to things in the corona. And in fact, it has a spectroscopic and a solar wind in situ measurement kind of signature, which is pretty credible. And so but the main thing is that the corona is well mixed. And this was not anticipated at the time. In fact, they talked about things like the calcium chromosphere, like there was something made of calcium going out from this thing. This is early on. So again, now during the 1940s, then shortly after this, or around the same time, we have Ernst Alfvén and others, and they were able to show, even by then, that qualitatively, and they asked, the question was asked, if the corona possesses so little friction, why is it so hot? One proposal was acoustic shocks. We now know that not to be the case. Basically, by the end of the 1940s, we knew that we had magnetism that was frozen into the, on any observable scale, into the plasma and vice versa. So a piece of plasma identifies a flux tube, and a flux tube forever is filled with this one and other pieces of plasma, never to change. And so what's interesting from here is that they also started MHD. That was Alfvén, who came not to believe in it, and then there was a mechanism by which you could generate within an ideal plasma something that would dissipate the energy. The structure was an acoustic shock, slow mode in the case of low beta plasma. In the 1950s, various things came together, and this is now the major focus of solar physics, I would say, is if you can find a paper that doesn't mention reconnection and the outside of the sun, then you're pretty lucky or unlucky. There's a huge belief, and I think bias towards reconnection as the thing that's heating the solar corona. That doesn't have to be the case. In fact, I don't believe it is the case now, but that's a subjective opinion, and future research will solve that. Nevertheless, the major concepts here was that now we have a way through a clever way of bringing magnetic fields of opposite sign together. Sun is untidy. They're bound to happen. You can't always align the magnetic field, and that's a good thing, otherwise it wouldn't do anything. So what we have here is a picture that when you change the topology of the magnetic field, remember I said frozen fields means one and forever. A donut is a donut forever and all time. Now we can take the donut and tie it up into a pretzel. We've got something more complicated, and in doing that, we have a way in which some energy from the magnetic field is converted into motions, because what was previously equilibrium with Lorentz forces under some kind of balance, turns out that the travel time across the corona is very small in terms of equilibrium of forces. So and that's seconds or something. Then if we see things going on the sun, and particularly in the sun's corona, something is doing that, and reconnection on the scales we observe is the answer to that. So we have a way now to convert magnetic to kinetic energy in heating. So the only question is it compatible with the observations of the solar corona? In the and here comes our first real picture of how old this guy was, Keith Richards. That's what he looked like in the 1960s. So again, he's 23 years old or something here. So now we come into what I consider to be a slightly more mature age about understanding all the zeroth order processes that we need to understand to appreciate what the plasma and the corona is doing, okay? Then along comes Skylab, and we see these beautiful pictures of loops systems, and they just about have the resolution enough. There were rocket flights before this that showed similar looking things, but slightly not so good. But Skylab had the imaging and duration. I mean, it lasted many months in 73 and 74. It came down and landed on some poor Australians' heads about, what, 20 years ago now, I think, or something. One hell of a big thing, this. I mean, you can see it. You can see you can actually go into this mock-up of the Skylab in the National Aerospace Museum. I mean, it's very roomy and comfortable. I mean, it's very good. Okay. So what did Skylab tell us? Well, the classic paper that's cited is of one-dimensional coronal building blocks, RTV. Those of you in coronal physics will recognize this. What is this saying? Well, the plasma's frozen into the magnetic field on observable scales. It seems to be organized so that I put a little bar magnet underneath the surface of the sun, generated by some kind of hydromagnetic dynamo, and the stuff comes out the top, but it's organized such that what we see is heated, and this is X-rays, remember, so no heating would be white in this figure. Darker is hotter, is brighter, and so, but these aren't diffuse. These things are organized into, these things we call loops. And it's an unfortunate word because if you look at the hoops that little girls and boys ran along the streets with in Victorian times, or with pneumatic bicycle tires, you think of them as having a circular cross section, but there's no reason to assume that's the case. There never has been a reason, and in fact, I don't think it's true at all. Nevertheless, that's prompted a lot of people to do a lot of analytical work based upon a high degree of symmetry, which is just not present. And in fact, it denies the possibility of forming small scale structures that would dissipate to a larger degree. So by adopting applied mathematics and doing your algebra, you're really not going to get to the heart of this problem. Instead, what we have is a picture where you have a time average magnetic field, which would look like the picture on the bottom right. Here's the equation. And that evolves on time scales from days to hours, flux emergence, whatever is going on. And you see these things heated, but the actual dynamics that's actually doing the heating is unobservable. This is my claim. So this is what we're talking about. I don't think it's fruitful to consider the observations of a moving corona as the same thing as the heating problem. This is one of my conclusions. Okay. In 1978, and here he's looking a bit more, well, a bit more 70s, right? He's got the haircut and all that, and attitude going on. But now he's 35 years old. And the first absolutely complete linear theory was developed for this, concerning the propagation of perturbations with a variety of with motions that were observed underneath, and allowing those and assuming that same perturbations that seen at the photosphere with photospheric dynamics occur at the chromosphere and above, so that the chromosphere hasn't really changed things too much. That's the assumption here. So you just apply a power spectrum here, do your linear calculations for the dissipation, the generation of resonances in a linear approximation. Once the resonances have come along, where you have the waves motions happen to be at the local alpine speed, then you generate enormous amplitudes in your waves, which is sufficient along different pieces of plasma that belong to different parts of. There's no reason to assume it's homogeneous across this thing. In fact, this won't work. And the breakthrough idea was that there's a gradient in the cross field alpine speed that you can tap into, such that any given frequency is probably going to find a place in this gradient to heat the plasma. So it was a complete theory. Unrelated at the time, of the same year though, is the finding by Athena White that acoustic modes just don't have enough energy. And this was done on the basis of looking at the top of the chromosphere, looking at the available kinetic energy in waves and other motions, putting in a model density and saying, what's the energy flux? And it falls short by a factor of 50 or something. So, and even so, we would have said on the basis of a picture like that, what on earth has acoustic energy got to do with that? It could be that it channels acoustic energy with slow modes up the field lines, but these guys basically said, no, that can't happen. He's getting a bit more, looking a bit more wild around the eyes now. In the 1980s and 90s, I suppose his lifestyle was starting to take up, some of his resources. But he's not quite dead yet. He's certainly not dead now, as far as I know. But in this period, we had various things going on which were of great interest to people in this field. And we started to see, on the basis of resolved observations, lots and lots of inferences about coronal heating. Essentially, all of those have contingencies. So nobody's, aside from this reputation of acoustic modes, what we're doing here is people are being creative and wonderfully creative. They're coming up with all kinds of ideas on how to get the energy from these large scales into small scales by looking at things on the very large scales alone. And one of the things that they did was they noticed that Parker in particular has made it very, very simple kind of idea that you have to move, if you have a vertical field line, you have to move sideways in order to get any kind of energy generated that can go up in an alpha wave. Acoustic waves can't do it. Fast modes, I don't know what those are, but those would not account for that structure we see here. They go all over the place and tend to go towards places where the density is lower, not the density is higher. So the intermediate modes, the alphane modes, are the ones which we consider, and by that, it could be slow evolution. It's just the alphane mode is then transmits the information about the stresses very quickly, and you have a quasi-static evolution. So I talk about alphane mode simply not as a wave heating, but as a way in which you modify the structure in the upper in the corona from motions beneath. And so that equation there with the B perp is B parallel. The B perp is the critical thing here, because B perp, as we see, the stress on the magnetic field is B perp times B parallel. And if B perp is 0, in other words, if we have a time average magnetic field and we perturb it along that magnetic field, there's no contribution to the pointing flux, no contribution at all. And so we have to have a little tiny B perp being generated. And if you have a sideways motion on the surface like granules, you can stretch the magnetic field and convert a B parallel into a B perp on the left, and then you get yourself a stress there, which does work. And now you have to get rid of that work in the corona, and that's the heating rate that you get. So the magnetic field that we observe on large scales is definitely something that you need to look at in order, when you do work on it, to generate alphane waves and to generate energy going upwards into the atmosphere. So, but what's going on here is that there's no reconnection involving B parallel here that I'm envisaging. It's only the components of B perp which are a part of the heating mechanism. This is what I will try to argue. So from 2000 to today, I'm gonna show my biases here. I was just talking to Maurice earlier today, and he was talking about how much more he enjoyed reading the old papers than the new ones. And because of their pedagogical slant, and also you feel like you've got an organization that's not too specialized yet. I think one of the tragedies of over specialization is that we end up spinning our wheels. And you can read these things here. They're all talked about in the book. And so I'll go into these. But basically, if we just look at the last point, my conclusion, and again, it's subjective, and everybody's welcome to their opinions. I had the opportunity to write a book, and so I did. And we have, what I conclude is that we actually have weak methodologies in coronal physics. We have extrapolations, we have ad hoc models, we invent a certain number of parameters that we need to fit the data. So the loops don't look like an RTV loop. What do? Oh, we pretend it's full of little tiny loops, all different RTV loops, and we fit that. I don't regard that as science. I mean, you're not refuting anything. This is going to be hard to hear for some people, that they have been working on a problem which doesn't lead anywhere, in my view. And it certainly is up for debate. Incomplete simulations. What do I mean by that? You can't do a 7 order of magnitude 3D simulation with all the physics we know. We think we know pretty much all the physics that we would need to in parts of the problem. On MHD scales, there are various codes listed there that do this. And then on sub-MHD scales, we have an entirely different kind of physics going on. And so that in that sense, the simulations are complete. They may well be correct. All the answers to coronal heating could already be in these codes. That's a possibility. But it's not a proof. In fact, there is no proof. You can only disprove, and that will be one of my major messages here. There's a lot of focus on the events. The event of so-and-so. By definition, if you're looking at an event, you're not looking at the coronal heating problem directly, because there's a hell of a lot of the sun that doesn't do a damn thing while it's heating the corona. And if you want, you can look at the corona and say, oh, how dynamic it is. But if you've looked at those pictures from EUI instrument, you can sit and look at it, and 99.9% of those pixels do nothing on a time scale of half an hour. Your eye is drawn to things. Confirmation bias, activity, coronal heating. I don't see that. All kinds of speculations. And so what we end up with is an embarrassment of riches. This is a paper from 2000, which is a very honest assessment of various kinds of ways in which B parallel is turned into B perp, and so B enters into your scaling law for heating here. Multiple hypotheses are tested: critical angle, critical twist, current layers, current sheets, Taylor relaxation, turbulence with constant dissipation, closure spectrum. Basically, these are all compatibility tests. That's all it is. Because you haven't refuted any of these things with the data. To show you that, here is the comparison of each model, a parameter of each model with a measured parameter, as best they could do it. This is an honest to God, really nice piece of work. I'm not bashing it at all. I think it's really good. And that's the honest part. 2 of those models might be refuted on the basis of the statistics here. Another view of the riches, we have all these wonderful words and multiple qualitative conjectures, and all based on observations above 200 and mostly above 1,000 kilometers, and essentially no refutations. Okay. I don't regard this as an advancement at all. I think it's just going in and generating all these ideas. And like I said, it's been very creative, but I don't think it's very important. I want to comment on the use of numerical experiments versus simulations. What I call it a simulation is something intended explicitly to compare with observations. And what I think you'll see now is, if you believe that there are 7 orders of magnitude difference between what we want to know and where the energy is heated, is where the dissipation, the irreversible process is happening, then this is probably not going to succeed. And yet this is where 90% of the advances in coronal heating are being published. What do? You take some data, STO. You take a code, Muran, you take defrost, you compare the 2 and you publish a paper. So think about what the outcomes of this process could be. The observations are just insufficient. In other words, you observe the corona at Mauna Loa, except there are clouds. That, for instance, is an observation that's not going to tell you anything. The data are then unpublishable, with a possible exception that if you've got a new instrument, you can probably get it into Nature or Science. That's a very facetious comment, but it's true. If you have a new instrument, it's easy to get into Nature or Science. And as we know, nature and science are what, 70% wrong? So why do we bother with nature and science? I honestly don't know. And I'm being cruel, but you know, observations support parts of the model. Oh man, now we're in business. We can publish as much as we like. AppJ, monthly notices, ANA, JGR, well, you know, just we go through the roof publishing everything. But we have these contingent results. And I've got quotes in the book from a whole variety of papers that say, these are compatible with that, but we can't discount this. I don't really regard that as progress. The observations really support the model. Oh, man. Now we even go to the New York Times. We're done. Except we're not done because we keep doing this kind of research and applying for grants. Now, the observations refute the model, i.e. we get a negative result. That's really hard to publish, generally speaking. There are exceptions, but they're in the minority compared with what we see. I think that's the most important result you can ever get out of an experiment. Should 3 be our goal? I don't think so. If we reproduce the data, my God, we're in real trouble. And what's going on here is we produce data that are not critical. That's what's going on. That's the problem here. So the conclusions I come to are that we have great difficulties here. So what are the lessons learned? And we're coming to the point where I'm going to show you a couple examples of the kind of research that I've been doing that I think would be better. The magnetic paradigm for sure has survived multiple challenges. I don't think anybody would say the corona is heated by pineapples, like Tom Ayers said, or by nuclear reactions that, you know, proposed in 1930 or something. By observing UV X-rays, generally speaking, we're seeing only the after effects. It's like looking at the lights on a Christmas tree and figuring out how the lights got there in the first place. I mean, it's not particularly useful for this problem. It's incredibly useful if you want to understand dynamics of the plasma, but that's not the same problem here. The problem is explicit. We have energy generation, transport, and irreversible dissipation. It may be that on the way, dynamics is important, but we've yet to demonstrate that. The plasma is intrinsically untidy, and this is a critical component of physics of the coronal heating. You're never going to get a homogeneous plasma that's in a low beta state that is going to be easy. There are instabilities which can occur, but if you start from a state where it's in thermal equilibrium, it's just going to cool off and drain out. So you've got no information at all on what actually led to this situation in the first place, which is what we're trying to find out. The energy is a particularly weak constraint. Very often, there's enough energy in spicules, enough energy in bananas, there's enough energy in whatever it is you want to heat the corona. But you don't hardly need any downed energy. It's a very, very weak. It is a critical constraint, but the observations that we make are at densities that are so high that even the tiniest amount of motion is going to overwhelm the entire energy needs of the corona. One of the things that is in the book, and I don't have time to say this, but if you have, one of the things that strikes me about the corona is here we have a system with a 2,000 kilometer a second alpha speed. And yet we observe line profiles that are 10, 20 kilometers a second wide.
Yeah.
That I think is really important. Any reconnection on observable scales is going to produce something close to the alpha speed. That's just not right. It's not right, and it's been misleading us for quite some time. Simulations versus data. I already talked about that. I don't know what to do with those conclusions. Confirmation bias must give way to reputation, and the approach should be to make robust physical predictions as best you can, challenged with information-rich data. Okay. And what's rich? It's maybe a question of taste, but what I would call rich is the line profiles. If you're measuring 20, 30 kilometers per second, even in active regions of line widths, why would you expect that physical reconnection of major components of the magnetic field could possibly be compatible. We should see things at hundreds of kilometers a second. Sometimes we do, but those things we call flares, and yet a flare can go off, and the coronal and the heating is going on before and after the flare with no particularly different outcome, and yet this flare's gone off, and people say the flares are heating the corona. I think that's troublesome. So, in getting towards the end here, the working assumption that people have is implicit, sometimes explicit, is that, quote, high-resolution observations are information-rich. But 4 of the 7 decades of scales are inaccessible. Thermal data measure the effects of the, not causes. Your cake is already cooked, and you're eating it, and you've got to find out what the recipe was that made it. The methodology of simulations versus data is the predominant form of publication I see nowadays in coronal heating. And that is just not, I don't think, producing definitive results. And I would love to hear, I'm sure people will disagree, and I'd love to hear whether we can actually get rid of things, ideas. And then there's this very nice quote: reproducing reality in models does not necessarily mean that we have an understanding of the mechanism. And I know all the people that build the models completely know. I mean, everybody knows this, except that it's kind of guiding what people actually do. So there's a disconnect between what people believe and what they end up doing. And so many young people now are given codes to run in order to understand something, like inversions. Honestly, I don't think this has a place in physics. It probably has a place in solar physics, because solar physics is not the same as physics. And we all know that we all need a job, and we got to get grants, and we got to do this stuff. So I'm talking from a very idealistic point of view here. I mean, that's sort of who I am. I mean, you know, there are some opera singers I think are fantastic, and other ones that make me feel like they're dragging their fingers against the blackboard. So, you know, one of the ways to combat this is to acknowledge what central issues are in heating the corona. I want to test the hypothesis that the time-averaged magnetic field is simply passive. Peter Starrett pointed this out in 1999, asked the question. And that what's really going on is the active part of the coronal heating is actually the perturbations of that. Is the plasma thermal? There's no reason it should be. The mean free path of an electron in a 1 million degree plasma is 2 megameters. If you go to 3 million degrees, it goes up by a factor of 10. And that's if you're in the sort of core of the distribution. But if you have ability to generate non-thermal electrons, damn it, those things just never going to interact with anything. They're going to go back and forwards until finally they have a collision. So the fact that we're dealing with a plasma and that the cross sections go as energy to the -2 means that we better sort of pay attention to that to see what the consequences might be. There's one test you can do based upon nearly thermal plasmas, and that is you can find out ion viscous heating is really dominating before you get to the kinetic regime. That would be really interesting to find out. The line profiles that I've seen in the ions that we observe almost never have wings on them. But then the thing is, we haven't had sensitive enough instruments to look for them yet. So, and the fact that it's just 10 kilometers a second in the line width, 10 to 20, with an alpha speed of 1,000 is telling us something about this. So what I want to do is try and go through the range of things that can happen as you go down in scale and see which ones you can keep and which ones you don't. I think refutations are important. I'll go over a couple of them in a moment. And then one of the things that I think is really important in refuting models is, in order to refute a model, you have to have a model. It's a stupid thing to say. It's an obvious thing to say. You don't necessarily have to have a model. You can have a hypothesis and try and use arguments to see whether that hypothesis makes sense. That's what was done in the early parts of the studies of these things. In terms of religious belief in statistics, I think that Bayesian methods offer something much more powerful, but they're not a panacea. You have to be careful about how you define your priors. You have to be, there's all kinds of problems with it. But what it does do, it forces you to make a decision about what you're going to test. Because you have to have a prior, and then you use the data to modify that prior to get the posterior. And it could be that multiple processes are heating the corona, and then you can make multiple priors, and you can make an array of priors with a matrix of observations, and then get your array of posteriors at the end and find out, well, spicules really didn't do that, or this did that, or this didn't do that. So I'm talking about philosophy here quite a bit, and I think that's where we skipped over some difficult issues in this area of research, which is concerned with remote sensing. That's basically part of the problem. So one of the things I think we should do is observe, try to build an instrument that could observe very high angular resolution structures in the corona and active regions. I mean, the highest resolution we've got is 200 kilometers at the moment, but those are with instruments that are at least 7 times the diffraction limit. That's not the problem. You could build an instrument in principle with a very much smaller pixel size. The problem is stability of the aircraft, of the spacecraft, right? So if you're integrating and it's wobbling around, even a tiny amount, 20 kilometers on the sun corresponds to 0.04 arc seconds of sun. That's what it is. But the idea that you will not see anything if you go to higher resolution is just flat out wrong. Because if you go to higher resolution, you have a lot of zeros, but you have higher counts in the places where the structures are. And that's illustrated with this one here. So this is a definitive test of the natural size of the smallest structures in the corona. If we can show that it's really 200 kilometers, we don't have to worry about kinetic process, at least to 0th order, in heating the corona. I recently published a paper based upon only on the idea of trying to study how dynamic the corona is. And what this shows you is an average image of an active region. Active means dynamic. Everybody knows the sun is really dynamic, dominated by dynamic. The whole corona is all dynamic all the time. And so what I did here was just color line everything very accurately, and then take power spectra. Didn't even do wavelengths, didn't feel the need to. And what I found was there are circles where you have a lot of activity fast. Those are all associated with observable flux emergence. The ones that aren't doing anything dominate the area. There's stuff going on in at moderate frequency. You can hear the foot points. But what I found here was that if I assumed that energy was released in little bits every so often, like in the nanoflare picture, that was inconsistent with the observations of the top of these coronal loops. And I think that Parker made an error in his original nanoflare paper where he was talking about random foot point motions, but he just simply added up linearly when evaluating U perp and V perp, V perp, he added them up linearly instead of at random. And so you have square root of a number you have a square root as opposed to a linear number. And so my picture is that Parker was right. If flares dominate the heating, remember it could be just some other process, or except that these have to be on picoflare scales. The other thing I did recently was with DKIST and with Greece on the Gregor instrument, is to not look at the photosphere. Almost everybody has examined the connection of the corona to the photosphere. Those differ by 6 orders of magnitude. Yeah, something like that in pressure. Yeah, really, it's like looking at the ground and then observing the ionosphere to say is this connected to the ionosphere. That's sort of the equivalent thing. What I did was instead use observations of the chromosphere and the magnetic field there and the motions that we see there, and try to compute a proxy for the pointing flux. And in these yellow and blue circles, you can see two places where I have a loop and one where I don't have a loop, where the pointing flux is larger in the one that does not have a loop. There's basically no correlation between these loop foot points and what's coming out of the chromosphere and going up. That's the kind of observation. Here's another one. Look at all that magnetic field at the top. That's the line of sight magnetic field measured during a campaign with DKIST. And it's just one of 5, and all the data look like this. The bottom is the pointing flux. It's very noisy. It's not surprising because you've got to, this is at the limit of what we've been able to do with the first observations of DKIST. But what this is telling me is there's whole lots of the corona. Most of it is empty of bright emission, and these have to be 171, but all the channels of SDO show this. They're morphologically the same. So there's basically no relation between pointing flux and the corona. Pointing flux is not perfect. It's a very impure thing. It's even a scalar. I don't know whether it's going up or down. It's just that relative across the surface, there's no relationship between that quantity and what we see overlying in the corona. So the recommendations I would make at the end of this talk are, first of all, adopt a physics-based approach. And I think everybody would say this is probably a good idea. What do I mean by that specifically? I mean, acknowledge that you're not observing the 4 orders of magnitude down towards the dissipation scales, and try to find a way to examine things that are independent of resolution, for instance. Okay. Observe numerical experiments. Don't compare them directly with observations. I think that's a fruitless task for coronal heating. For coronal dynamics, you might well learn one hell of a lot. It might be perfect. But the coronal heating problem is a subset of the coronal problem. And let's not confuse the dynamics that we observe on large scales with what's going on the small scales. Seek really robust, information-rich physical signatures of heating mechanisms. By that, I mean, if you've got a U sideways doing work on magnetic field lines, sending stresses up and then dissipating, if you can figure this out and then figure this out, you're going to, and then look at how the light coming from this thing is going to be measured in your instrument. Then you can build a Bayesian prior that would say, is this compatible with this or this incompatible with that? And you make progress there. There is something that people call turbulence, which everybody goes, oh my God, you know, it's turbulent, we're dead in the water. The theory of MHD turbulence is actually quite well understood now. It's very anisotropic. All the turbulence is going on across the field lines. And there are wonderful, elaborate theories now where you generate small scale structures in velocity and real space, and you end up with predictions, solid predictions out of these analytical models, which have been built upon empirical understanding of calculations and measurements of, say, the solar wind. Those are the 2 places where this LHD turbulence really comes from. We should also adopt refutation as a primary methodology. The young people must challenge accepted wisdom. Don't believe anything. Do it yourself. Go back to Newton's laws, go back to Spitzer conductivities, go back to look at the nature of, you know, those things. And just because somebody says nanoflares heat the corona, we're going to study nanoflares, I don't think those things probably exist at this point. But don't prove me wrong. Be bold. Try to go out and change the subject. Do the work you need to succeed as a researcher in this area. But 30 odd years ago, I was given this opportunity, and this is the net result of that. And what you'll see is I've got negative results. So you say, well, I've got nowhere. No, in fact, I would claim that if I'm right in those situations where I've observed data that aren't compatible with nanoflares and aren't compatible with the idea of 1 pointing flux in equals 1 coronal heating loop out, then that's progress. Negative results are progress in this field. There's only one authority, that's nature. Shouldn't have too much respect for people like me. Make your own mind up. Just really enjoy what you're doing. And if you see something like an oddity or unanticipated behavior, why the hell would the sun do that? Go for it. It may make perfect sense to somebody in some lab somewhere, but the most solar physicists, you know, it might not be noticed. So, and that's all I have to say. Thank you for your time. I will play a movie here while we're relaxing. Stop there.